Welcome to the Control Engineering webcast, Digital Engineering, Designing Today's Modern Machine, sponsored by Rockwell Automation. I'm your moderator, Mark Hosky, and I'm happy to join you today on behalf of Control Engineering. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of the webcast by adjusting the volume on the computer or by adjusting the volume on the webcast platform. If you're having technical problems with the audio or the slide presentation, click on the question mark at the top right corner of the screen to access a list of system checks to try before connecting to an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Type questions for our presenters in the Ask a Question box on the left side of the screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email within a week with the link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of the screen. Those documents also will be available with the on-demand version of the webcast. I'm happy to introduce today's presenters, Matt Masaryk and Antun Lane. Matt is currently the Control Software Business Manager at Rockwell Automation, responsible for the development of a portfolio that includes design software, communications, controller emulation, and more. Matt has held roles at Rockwell Automation's marketing as well as sales teams, where he worked firsthand learning from users and bringing new technologies to market. Antun brings more than 35 years of industrial automation and control systems hardware and software integration experience within his focused role of product manager for digital engineering. Antun is responsible for the advancement of key technologies within Rockwell Automation and partners that enable the digital thread with a current focus on Emulate 3D. Thank you for joining us today, gentlemen. Now I'll hand it over to you.
Thanks, Matt.
Thanks, Mark. I'll get us started here. So thank you for such a warm introduction, Mark. As Mark said, my name is Matt, and I'll be kicking us off for the first few slides, and then Antun and I will be co-presenting for the rest of the way. We're going to start with an introduction not just to ourselves, but also to kind of the current state, to start with the foundation of why we're talking about digital engineering, what this thing is. We'll walk through the investment momentum, what the leaders are doing, but then also what this space ultimately delivers. And then we'll talk a bit about how design is actually evolving. So a bit of definition for what digital engineering is and what it contains. And then really, we're going to spend a lot of time on item 3 there. We're going to walk through a project, both comparing it to its historical process and procedures, but really we want to dig into what a hypothetical project would look like if we applied digital engineering from start to finish. And then we'll wrap up with some Q&A. So I'll get us started with a bit of a background. You know, when we look at digital transformation, digital engineering, plenty of terms. The reason why we're talking about this so much right now is that we know that the current state of manufacturing is really ripe for improvement, both in new projects as well as investment in historical install base. We know that downtime is extremely expensive, and we know that this is a topic that every customer and every company in manufacturing is taking a look at. Layer on top of that, a bit of a skills gap, transformational technologies, higher demands, shifting workforce, all of these really create a need for looking at our projects and our investments differently. So when we look at what the investments for digital and how this momentum is actually transitioning into practice, we know that 50% of the manufacturing industry today is powered by some sort of smart connected system. So a few years ago, we were talking about the rise of devices and connectivity. Well, that's here now. So we know that we have this smart manufacturing rise that is part of our daily infrastructure. And we also know that digital engineering as part of a design practice and operations and maintenance practice is growing significantly to shore up both the skills gap as well as the technology gap to squeeze out those inefficiencies in our design as well as operations. And with that comes significant investment in time and money. Of those organizations that are leading the way in IoT or digital transformation. 75% of them are already admitting that they're using some form of digital twin or plan to within a year. We're going to define a bit of a digital twin here because that can mean a bit of a different thing depending on your context or application. But the simplest way to think of it is a digital twin is that digital representation of a physical asset. That physical asset could be a machine or a set of machines or a cell or a line, or it could be our entire facility. It doesn't really matter, and we're going to look at what that means across a project, and that will mean something different for each person or for each application. So finally, this is really going to be our roadmap for today. We're going to talk about what leaders are doing, or what we would be doing if we were a leader in manufacturing in our hypothetical project that Anthony and I are going to work through. And we're going to start by looking at the vision of how we want that project to be laid out, and how we want to achieve success in driving time, effort, and efficiency into that project. We, as Rockwell Automation, look at this as an ecosystem because it's not just one technology that's going to enable this. So we'll walk through, yes, some technology from our portfolio as well as our partners, because this is a system-based approach. And depending on where in the project you want to achieve your success, you may be using a certain technology or the other. So that's really key when we talk through this, that it's not one piece of software or one piece of equipment that's going to achieve this. It's really twofold. Look at the project and which piece of it you want to focus on as your company, where you're going to drive efficiencies. And then what technology ultimately is your means to that end, and that's going to help you achieve that. So we're going to start at that front part and talk about the project first, and then we'll layer in the how. That bottom left piece is that these are some newer technologies. We'll talk about how really digital engineering, simulation, emulation, these are parts of a new discipline for a lot of folks. And with that takes time and attention to develop that skill set. And then we can't talk about going digital really without talking about the shift of the engineering mindset that this takes. Yeah, project layout and the sequence of events and how we actually organize our projects, certainly. But the skills that need developed, or the opportunity for a modern skill set to really deliver more for a project, is going to be front and center. So there's our foundation of just the investment, what the leaders are doing, and then how we want to shape for the next 45 minutes. And now we're going to transition a bit to look at what is a project today, and what does it mean to take that project and move it into the digital space. So largely, the engineering of the project isn't necessarily changing. It's how we're visioning and how we're looking at the steps and the dependencies and reliances that we have on our project to really question why they need to be arranged in that certain way, and how can we shorten design cycles, make them more efficient by spotting improvements, and moving as much as we can to the digital space, because that's where we can make rapid decisions, test, continuously improve, and simulate things before we have to rely on physical builds. So to move away from the status quo, what that means is we're going to break this into a couple different sections, but really you can think of this idea is the design and prototyping stage. So this is where we're really driving innovation, speeding up that design loop to test, continuously test, redesign, make improvements, do that as often and as frequent as we can, so that when we finalize that design, we've driven out all of those what if scenarios and we know exactly how our system is going to react and how it's going to perform. The second piece is once that project is designed, then we're on site. So now we're talking about the piece of a project that is extremely risky, and usually everyone raises their hand to say this is where they would like to drive out time and uncertainty and risk, which is commissioning, on-site, training, the reliance of travel, surprises when you're up against a deadline. That's where a lot of risk is, so that's a huge focus. And then this does not stop after that machine is turned on or that line is commissioned, then production starts. And really this whole piece is then a loop, because certainly once production starts, that's where you understand and have tweaks or new demands from a new design or a new requirement from a customer or a user, or you learn through the operation things that you wish you could have implemented in a design. So the production phase is equally valuable to then inform either a new design loop, a new design iteration, or the next generation of that system and machine and put that into practice. So as we talk through here, we'll break down the actual project, but those are three big buckets of value that we focus on. We say shift the status quo. These are the pieces that we think are up for grabs. Okay, so Anton, we've got the foundation built now. We're going to talk briefly about what the historic project is, or where are we coming from, because we're going to eventually go to a digital project. But this is largely a bird's eye view of where we've been, which is a very sequential, heavily dependent, stepped process in a project.
Yeah, absolutely. So as we progress, if we look at how we classically designed, we looked at what was our experience in the past. We relied on output trust, if you will, from others, rather than having real live data to decide on. And that makes it difficult, right? You want to be able, every situation is different, and if you can't try it out and prove it out, it becomes very difficult to rely on it, and you get unpleasant surprises later on. So doing that, getting the modeling engaged, even already at the design phase of a project, really helps to create a more robust solution overall. And then as we get into system design and automation design, at least historically, there was very little opportunity to experiment, right? Because it's very difficult to do to build complete prototypes and have those available in the engineering location. So often you can't make things work until everything is complete, and that makes it very complex to do any kind of early testing. The other thing we've seen, an area where we'll focus on, is mechanical engineering and automation engineering. Historically have been siloed, and mechanical design was thrown over the wall, and then electrical engineering had to pick it up. And we're trying to get to a workflow where we do much more collaborative work, right? Where we get part of the design, we work on it, we evaluate it, we provide feedback, and there's an opportunity to improve things. So, but that historically, very, very difficult to do. And then site work, getting on site and having to do commissioning is always been very painful. The biggest problem I've had when I did commissioning was I would be in the middle of commissioning a project, then you'd find a problem area, you'd say, hey, how do I need to fix this, but to fix this, I really need to do a redesign, and there's a customer breathing down your neck saying, hey, the mechanics is ready, why isn't this system running? So you go look for Band-Aids and chewing gum and chicken wire and things like that to go and get that system up and running to pass FAT. You're not interested in providing the best solution, if you will. So that's a big part of where we see challenges we saw challenges in the past. And then long term, that system is just a lot less reliable than it could have been if it had been designed correctly. The other thing is access to physical systems. We'll spend 50, 60, 70% of their time waiting for equipment to be available to them, right? Because we're there trying to test software, but others are there trying to finish the mechanical build, and yet others are concerned about having specific SKUs run through that may not use the station you're working on, all those kinds of things. And the same with training. If you have to train a customer on how to operate a line, you can't do that until the line is up and running, which means that for the commissioning, you need to bring all your own people in to get a properly skilled team to run that line. Whereas if you had a chance to train customers earlier, you would benefit from that by saying, hey, let's use the customer's engineering team that is on site anyway, because they're the operators, rather than our team flying in from wherever we're coming. And then analyze and optimize. Yeah, whenever you get a new set of SKUs or modifications to any kind of a design, you need to go and do that on the production. But you can't do that because the line is up and running. So again, you're making all kinds of assumptions. I had one customer who actually had 11 parallel production lines all making the same thing. And 10 were focused on production, and 1 was focused on testing new SKUs and new design modifications. And they hated it because they lost 10% of their production capacity simply on that prototyping line. So, yeah. Yeah.
I was going to say, I mean, I think my big takeaway, Antun, too, is that through no fault of the history is that you can't commission until it's built. You can't test until it's built. You can't build until it's designed. We have these reliances, and that's what we talk about status quo change. That's what now we have to rethink. And if I had a consistent space that acted exactly like my real asset will eventually, and instead of reordering parts, I am clicking a new model element to change a motor or reconfigure or something, that's a drastically different experience than having to reconfigure a physical asset. So, as we transition now into our digital project, this is where we say, here are the pieces that are sort of our gut checks of are we embracing the digital side of this? Because it's really not about just creating a model. So we have a few things flagged here. We have collaboration, where we expect parallel workflows, which you were describing. We touched on the middle block of that design system design, which is we expect that this enables more experimentation, because that's extremely risky with a physical system, that you either don't have the time or the risk appetite to potentially experiment with something that doesn't work. Now we're talking about clicks rather than reorders and recutting steel. When we get to that operate stage, that's where, or at least the initial testing, that's where you're talking about the improvements that are extremely expensive to either band-aid or fix late in a project. But if you could run the system on your PC before you get to the site and before it's actually built, now you're talking about changing those improvements earlier in the process, which is much more cost effective and ultimately yields a better machine. And then the last piece here is that the technology side, this is pretty expansive. We'll talk about the digital twin asset, but this opens up new doors to then expand, which we'll touch on with partners for advanced simulation for maybe complex applications, go deeper into a specific part of your process that you need high fidelity, super clear modeling, or partner with, as you mentioned, connecting the electrical and mechanical pieces of our companies that are silos that may not always talk together. That's where partner technologies really come into play, that this turns into a really an enterprise or a system-wide view of design.
Yeah.
So let's go in, let's compare the slide we were just on, which is a very sequential, highly dependent design or project. And to walk us through now, if we, this was just our take on kind of what the pieces that we would rearrange if we were going digital, we were really diving into this with both feet. What things do we think we could get done in parallel and how they actually interact with each other? So certainly shortening our design time, but also now we're working, or multiple teams are working in a collaborative manner.
Yeah, so we're looking to bring really the concurrent engineering between controls engineering and automations and mechanical engineering all together in the same path, right? There has to be a basic design of the system has to be done, but once that is done, we get the opportunity for all these feedback loops between the teams, right? We can go and we can test concepts and play those back, and because we are not relying on physical equipment being constructed, but just simply CAD drawings being ready and connecting those into the controls approaches, we can much earlier discover how we can prove that, prove the designs or optimize the designs. We often find things that we say, maybe not quite the way we really, it doesn't work the way we hoped it would. How can we solve that? Either by a different control strategy or by mechanical adjustments, right?
Yeah, and you mentioned on the historic side, how much early on in a project is really a lot of trust. Hey, we've done this before, or you need to show me and tell me that you've done this in my application before. It's great. Certainly a lot of historical credit into folks that have a specialization and have done these projects. still not nearly as good as I will show you this application, and I'm going to show it to you with even your production constraints or your environments or the conditions that we expect to operate in. I'm going to show you this design working. Yeah, probably early on it's a little rough around the edges because we're going to show the conceptual side of this, and then let that model mature so that all along the way you're continuously viewing your system under the conditions that it'll operate in. That's a little bit more than trust. That's data.
Yeah, absolutely. Yeah. And then as we, so this again highlights bringing mechanical and electrical much closer together, much earlier in the model space, and then being able to do that continuous testing is fantastic, right? I don't want to have to redo my engineering every time. So what we do in the workflow in this scenario is we receive some drawings from mechanical engineering. We will mark those up and get them ready for controls testing, and we'll play that markup back to mechanical engineering so that when mechanical makes a change, we receive the marked up model back so we can quite easily adapt to the changes they've made. You don't have to redo all the markup every step of the way, right? So for very interactive designs, and we'll come to it in a little bit, the interaction with CAD is very, very important. And then we're built. Okay. So the training, the commissioning, and the startup, we typically would start once the control testing has been done and we're almost ready to go on site, we can already start training local operators. So people know what machine is coming their way and they can help us with the commissioning. But the commissioning itself, we can do, it's much safer, right? And there's much more things we can do that we will have prepared. You don't run into logical errors on sequencing or logical errors on operating philosophy. You still run into typical commissioning errors like wiring is wrong or calibration is wrong or bits and pieces, but the chances that you take a robot and you put it in run mode and it runs away and hits a wall and breaks some expensive tooling or worse is much less if you have had a chance to do your controls testing prior to that. And then in operation and maintenance, when we have our data twin and we keep it available, it becomes much easier to do the testing of those different SKUs, those different procedures, those line enhancements against the model before we shut down the line and say, let's implement them on here, right? So our confidence level of our changes will work is so much higher when we are able to pre-validate. So.
Yeah, I love that idea of confidence. You know, higher confidence up front, but then we're building on that as we go because we've continuously seen our design operating and testing throughout the entire cycle. There's no cross your fingers, wired up for the first time on site, or you know when you're ready for your FAT. You've done this dozens of times by that point because you've tested this. So if these are the concepts kind of as this project takes shape, these are the concepts that we're going to be applying. We're going to dig in now to kind of these groups, and we'll start with the concept and proposal phase. So early on, we talked about your reliance on trust, but you would love to be able to demonstrate and prove out a concept or a proposal to really set yourself apart, you know, from a user confidence that you're making the right decision, from a systems integrator or a machine builder or a line integrator perspective. You want to win the business, and you're going to do that by the lowest risk, highest ROI, clearest decision that you can make for your customer. So the outcomes we want to achieve here are, you know, demonstration focused concepts, a clear alignment between the user and the supplier, and then confidence in the choice and the proposal and the technology.
Yeah, it's very, very difficult for a customer to understand a 2D drawing, if you will, that shows all the components of a production cell like the one we're looking at, and know that, hey, this is going to meet my needs and going to meet my it's going to meet my needs, and I understand the flow of how things are happening in the system. And this particular cell is this. The picture we're looking at here is a typical outcome of a sales sequence at Cooper Systems, where they will build the cell, and then sales will use that cell to discuss with the customer and convince them that they've understood it. They can also go and show how the product will flow. It'll all be dynamic, and there's a much better system understanding among the different groups that care about this project.
So it's, I understand the needs that you have in your application, and I understand how I'm going to achieve that through these technologies and this arrangement, this concept and proposal. And don't just trust me. Here, I'll show it to you early on, earlier than you would, like you said, looking at 2D drawing, which doesn't necessarily convey the same approach.
Yeah, and you would be able to zoom in on any area that is unclear and say, this is exactly how we solve it here. Or, okay, you're concerned about that. Let's go into more detail on that particular aspect. It becomes much easier to zoom in and focus and have very clear sales dialogue.
Exactly. So we're through concept and proposal now. We're smarter. We have more confidence up front. We've been able to demonstrate that. Now the real fun begins, where we're going to start designing. And we mentioned how these are parallel, these are iterative, these are a shared space where we can have multiple teams collaborating and testing and experimenting again. So our outcomes here is we want to increase the experimentation with lower risk of that experimentation, shorten those design cycles because you don't have to wait for things to arrive for you to wire them up and test and actually build. And then earlier and more confident data on, are we achieving the performance that we want? Is everything operating as we had hoped?
Yeah.
So, Andrew, there's a bit of a spectrum here on what this design can take. At times we want to start on just basic simulation, and then you're going to talk us through all the way building up to a full virtual system.
Yeah. So we start with the core layout, the process simulation of those basic assets, and we need to understand. We want to start simple, right? When you do these projects, don't start with with all the details all around the model. Start with those things where you know there is high risk or high complexity, or things where things could easily go wrong, or things that you haven't done before, right? So don't try to boil the ocean when you pick this technology up at first. Focus on the core features and assume the rest will work. And then as you build experience with these digital twins, you can go and add more complexity. So here we're talking about, first we build the mechanical model of the system, from the CAD. We're animating the CAD to get get the mechanical movements done. Then we're going to add some of the PLC logic to run the aspects that we're interested. We can bring in the HMI and we model that part of the logic, and we build that up as we start. And then eventually we end up being able to expand that model. And it probably won't be on your first project, but on your second or your third, where you bring in detailed device simulations where that adds value to the model. Electrical system modeling, so we can go and we can say, bring in the wiring that is in the panel, model that, and validate that your electrical drawings are correct. Most often when there's electrical problems, it's not the electrician who wired it wrong. It's the electrical engineer who made a drawing mistake, right? So you also want to be able to focus on can my controller meet the performance? Can my network handle the traffic? So all those aspects come into play.
I think that was a great view, because we were looking at certain parts of my model. I may only care that I care about the time it takes to perform an operation. And then in the same model, but a different part of the application, I may really care about the mechanical performance down to a very finite detail. And that's the spectrum we're talking about, is that you'll build the fidelity that you need.
Yeah. And here, if we look at what does it take to do that mechanical markup, we're seeing here in Creo how the model is being marked up to indicate the degrees of freedom and the movements that happen. So we have a concept we call aspects, where we can make a joint, a kinematic joint, or a dynamic joint, or We can connect a motor to it or an actuator to make it move. We'll get photo eyes, we'll get sensors, we'll get all kinds of different aspects, right? And we mark those up based on the original CAD of the customer. Now we're looking at a bit of an odd example, but the point is you mark it up in Creo by the mechanical engineer who understands the mechanism, and he can just push a button and send that into Emulate 3D, which is our digital twin software. And then you can take it from there and do the rest of the animations, right? And I will highlight that it's important to get the mechanical engineer engaged in the process, that we do not just say, right, I'll give it to electrical. Yeah.
Yeah, this collaboration, but the key piece here is that the mechanical engineer at that point is making this CAD object model ready in his CAD platform. So there's no transition that he has to do or any sort of jarring that goes on regarding, he's in the environment that he knows. And then we're going to talk in 2 slides here about how those pieces all come together. But this is inside, in this case, Creo, an Emulate 3D toolbar that says, don't leave the environment, just make it model ready. And then eventually we're going to pull that in and it's going to be ready to operate inside of our model in our physics engine.
Yeah. So then, as Matt highlighted, we have the mechanical engineers use their own CAD packages if we can. If we have existing CAD that is, as legacy CAD, if you will, that's available, we can certainly import that. We have a host of different formats we support. In that case, it does get marked up inside Emulate 3D. But for companies like, or tools like Creo, like Inventor, like SolidWorks, like Onshape, the mechanical engineer can do it in his package and then export it to our environment, right? And we can go back and forth. As the mechanical engineer puts his mechanical markup on, after he has done that, it's sent to Emulate 3D. We add the electrical components to it. So motors, the sensors, things like that. And then we will save that back and push it back into the CAD environment, because typically the CAD environment is the master, if you will, for the models. And when a CAD update comes, you don't want to have to redo it, so you want to be able to push it back. So you get an updated set of, as the mechanical changes more, you retain all that electrical markup that you've done. Here's an example of doing things from multiple CAD sources, right? In this case, the OEM was very interested in the mechanics that took a car body and lifted it up off a vehicle. He was not interested in the design of the car itself, or not a lot in the design of the carrier. The carrier definitely has a role in the system, but that CAD from that car, that's a car designer. You're interested in the manufacturing piece of how is our movement to make that production work correctly, right? We're not interested in the design process the automotive designer went through. And yeah, you can find all kinds of interesting things, and we'll come back to that.
So you can focus on the mechanic or the CAD pieces of the model that you care about. Anything that you need, any kind of supporting or ancillary equipment, you can likely import it or work with a partner to connect into a single model space. And that really gets us through the mechanical piece of design. So we've got our concept and proposal, system and automation. Now we're kind of overlapping now, but now we have our system designed largely. We have our automation and the logic starting to be arranged. Now we can start to test our controls. So there's a key piece here is that if we're truly going digital and we're starting to layer in the logic or the automation devices around our mechanical pieces, we need to be able to test and automate and simulate those as well. So I'm showing now a piece of really a couple pieces coming together. So we have a Emulate 3D model, in this case, a manufacturing line at our facility. In the background, you see Logix Designer. You see my ladder logic executing based on this model. I see tags updating and flashing colors. So this system's running. And then the top right there, you see what looks like a controller dialog box, which is the controller emulator, which is powering this whole thing. So when we say digital, we mean all contained in the digital space, including the controller. So what that means is that we have to have a capable controller emulator that does more than just simulate, simple logic. And that's where FactoryTalk Logix Echo comes in. So this is another piece of technology that's going to contribute to this, which says if you don't need your motors to be physical and you don't need your conveyors to be physical, you don't need your controller for the sake of emulation and testing to be physical either. And that's where Logix Echo comes in. So the key pieces here, if you haven't seen it, it's a relatively new release, so you haven't missed anything. It's only been out about a year. But this is taking the entire same project as if you were going to download to a chassis that was sitting on your desk, but instead it's on your PC and you're sitting on your couch. You download the same project. Your IO tree is maintained, supports all the same instructions, but now we have emulated controllers that can connect to our digital twin, that can run our logic, all of this, again, without hardware. So there's a key piece here that is connectivity. So whether this controller emulator is just running our logic in our digital twin, great, big step, or it's connecting outwardly and actually sharing data with any other parts of our digital twin or our HMI, hopefully emulated HMI, or other pieces, that this becomes the nervous center of this Logix execution, just like a real controller. So the outcome here is that now we are really talking about a digital system. We can connect to other devices, we can emulate our HMI, we have our mechanical elements operating. Now we're really starting to feel like we're standing on the plant floor or standing in our facility right in front of our machine. So we've talked through the mechanical side, we've input our CAD, we've made the model ready, they behave by the physics engine that Emulate3D creates. Our logical design is ready, we have our controller that's also digital, that's going to be running our logic. The third leg of this stool is the electrical side of this. It's the electrical model that needs not only modeled, but done so, obviously in a digital space that has new capabilities and new efficiencies. And so, Anton, you're going to walk through the electrical side of this with Emulate3D's wiring manager.
Yeah. So we as we mentioned before, in these production lines, there are a lot of control panels, and they have mechanical functions, right, or hardwired electrical functions, but they take a lot more into account than only the PLC level I/O. All the permissives, all the hardwiring, ESOP circuits, enabler circuits, power supplies, things like that. So you can go and test much more of your model than just the PLC logic. It's really an interaction between the logic that's hardwired in the panel and the logic that's programmed in the controller, and where and how they are connected. And we have the emulation we're looking at right now lets us go into multiple levels. We build macros for all the individual devices that are in the panel. And doing that nesting is very convenient. We can visually see what's going to happen to the individual connections as they progress through. I think we're a little short on time, so I'm going to move on to the next step. But so here we have now included that electrical model as part of the overall puzzle, right? And it's all three are required to really do a proper digital twin, and that is what's used a lot in our automotive customers, but also in other industries. So with that, we get to a point where we're able to operate a complete machine, and we bring it into the training and commissioning side, right? So what we love and what I love, I would not do a project without this anymore, right? I wouldn't want to discover things on site. It is absolutely a nightmare. And as we do more of these projects, we also see more customers who say, don't bother coming on site until I have seen the software run against the digital twin, because I'm so tired of people coming on site and then really starting their development, right? Yes, basic stuff has been wired, but none of the logic has been thoroughly tested. And a job one can run out by 3, 6, 9 months because of problems with how all the individual suppliers have come together in the line. have done their level of implementation. And you'd love to trust people and say they're all going to come on site with working software. The reality is that seldom happens. So we see more and more customers saying, hey, all these 5 suppliers that are coming in to deliver this production line will have to make their systems work together in a digital twin environment before we let them come on site and do the actual startup, right? And that has tremendous impact on the startup times. We're seeing huge improvements at customers on the time to get to job one, right?
Yep. So, yeah, okay, perfect. So I was just going to say, let's look at the examples. So we've got the same AGV example with the auto body, but now we're going to see a way that we spotted a design flaw earlier. To your point, rather than getting on site, this one would have been really costly.
Yeah. So this is a presentation that one of our customers did to us at a recent user group meeting in the US, and they're specialized in automotive lines. And in this particular line, this vehicle, they discovered that the design of the carrier did not match the design of the car body. So the car body actually clashes with the vehicle on its way down, and you can visually see it, that pink oil pan, if you will, or the underbody cover, has been assembled too early in the process and collides with the vehicle, with the carrier. And because they found this during their virtual commissioning, they were able to adjust the procedures and make the system a success, right?
So in this case, we see it collide, and we spot that this would have been a very expensive mistake to discover on site if an auto body would have collided or clashed into an AGV. And we have a second example we're looking at, in this case, more of a metals mill.
Yeah, here's a billet press where we have the existing line, and there's an upgrade being planned. They want to make sure that the line itself is not down for a long time, so they literally have built a complete digital twin on this same production line. Then did their full controls upgrade, validated that it all met the same requirements, and hopefully we'll get to that piece of the video in a second. There it is. And then so they ran the entire digital twin on that same production line, and these people did it in no time. They actually ran it with an evaluation copy of the software, which is only valid for like 3 weeks, and they were able to get this system to a point where they could operate the HMI and operate the digital twin and pull off the validation of that application. They've subsequently bought a license, by the way. But,
well, how's that for low risk that, we're going to propose an upgrade and we've already run it before we've done anything. So we know exactly how it's going to work. That's really ideal. And so following these two examples, we got the automotive AGV example. We've got this billet turntable upgrade example. You mentioned the user group meeting, getting the stories and feedback, and we're not going to go through each one of these. We don't have the time, but this is feedback from folks that have applied this, and you see these buckets, kind of like we talked about earlier on: mechanical and electrical collaboration and validation, control design and test being faster, more often, and more efficient, and then the on-site experience, which I'll say includes commissioning and training and operations and startup and all of these pieces. There are a number of bullets here that just talk about the things that they've noticed or achieved that are in themselves valuable, let alone all from one company applying these principles.
Yeah.
Similarly, go ahead, Anthony.
No.
So I was going to say, similarly, if we look at actually projects done, there were 9 here from this, in this case, this OEM that said, I went back and I looked at my 9 most recent projects. The 7 of them, I had the time and customer appetite or demands to apply digital engineering here. So the dark blue part of this chart. And guess what? Of those 7, 4 of them were under budget. 3 of them were at budget, which is largely a success, but none of them went over or required extended time on site or commissioning or ultimately a high cost project to both the user and the supplier. Guess what? The two that they weren't able to apply these principles for, both went over budget. One went 3 weeks of extended support time that ultimately eats away any margin or ideally trust that is between the supplier and the user. And the second one went over by 4 weeks. So to them, the proof was in their results that they achieved.
And these were all similar automotive projects. So, yeah.
Mm-hmm. So just because we're short on time, we're going to quickly wrap up this last bit here. And when it comes to operation and maintenance, this is probably the part that's underestimated the most, because the value of the twin or the digital transformation doesn't stop at operations and startup. Now we're actually operating the system. And this could be its own other webinar of what happens after. But really, one thing we want to focus on is the wear and tear of a machine, as well as all of the discoveries or demands that change after that machine goes into commission. So you mentioned SKU changes, mechanical elements and their performance over time, the demands of just shifting and upgrading to newer technology. All of these pieces ultimately contribute to applying the same design loop back into the twin. And in this case, we're looking at a partner, Ansys, and using Twin Builder to look at the motor and its mechanical degradation over time, and being able to simulate that wear and tear and work that back into our project. So now we can actually look and say, I actually want to model the wear of my motor and know preemptively the conditions that it would create for a potential failure. So now we're talking about digital operations and informing that back to make smarter decisions. So because I want to make sure we have time for Q&A, to kind of wrap us up here, we talked about a couple pieces of digital engineering. Yeah, reducing overall project timelines. We saw that condensing going on by doing parallel workflows, expanding design possibilities because we want experimentation with really less risk earlier on in the project. And then that commissioning phase where we see so much improvement going on through time and risk. The technologies we talked about today, we mentioned Emulate 3D a couple times, showed the environment. That's really the nucleus, that physical model space where mechanical, electrical, and logic all collide. The very last piece I showed there with Ansys was our simulation interface, which connects third-party partner simulations like Ansys into our logic. And then I mentioned a few times FactoryTalk Logic Echo, which is our emulated controller to actually power and run the logic. So quick recap, and then we'll get to Q&A. This was our project that we walked through, Antu and Matt's hypothetical project here. We applied digital engineering principles kind of through these big blocks. We ultimately arrived at, we created a digital twin of our system that is a digital representation of a physical asset. But really that twin is a piece of a digital project, and the focus is flexibility, innovation, and reduce risk. So I think, Mark, we're right about at time where we want to be and make sure that we have time for questions. So I think we have a few queued up, and we'll spend the next 10 or so minutes talking and discussing.
Great, thanks so much. Now our presenters will answer questions from the audience. Type your questions for Matt and Antoon in the Ask a Question box on your screen, and we'll get to as many as time allows. Questions that we don't get to today will be posted online with the archive version of the webcast. Please remember to download a certificate of completion and a copy of the presentation by using the Event Resources tab on the left side of the screen. And on to the questions. So for the companies that have successfully executed projects like this, what are things that they have done that have made their adoption successful?
So I'll start quickly, Antu, and I know we both have thoughts on this one. So for me personally, I think what I've seen successful companies do when they're embarking on this journey is, I'd say two things. The first one is jumping to using the technologies we talked about is honestly probably the wrong move. The really successful companies first start with almost an internal self-audit, self-reflection, and say, where do I want to focus? You mentioned boiling the ocean, Antoon. The smart companies focus on one part of a project and say, this is our most inefficient, highest risk or highest cost. This is where most of our projects go off the tracks. For a lot of folks, that's commissioning, but they focus there and they define a problem. And then that's where they drive to an achievement early with that. And I think so identifying a clear problem for you, for your application is key. And then I'd say the second piece is successful companies have really treated this like a discipline, meaning, safety or networks. These are skill sets and concepts that aren't taken lightly. And they have folks who embrace and really dedicate themselves to this idea. And those folks have been wildly successful, where they have spent the time and attention to drive this as a solution for themselves.
Yeah. So I can think of a story of a customer who switched to digital twins when he was supplying a production line. It had 3 elements out of 3 of his different facilities. They were putting their line together. They came on site. All 3 of the machines are being built up, and a couple days before startup is supposed to really go wild, the project manager of the middle machine says to the guy up front, hey, can you put in that last piece of conveyor, please, so we can get the product flowing between these machines? And he turns around and says, that's not in my scope, that's in your scope. And that very simple problem cost them weeks of delay, right? And they said, never again. We have to go and figure this out in advance. We must know our drawings line up.
Yeah, how many times have we mentioned mechanical electrical collaboration here? Connecting those teams earlier, often, and consistently and constantly is a common theme. Yeah, great question.
Oh, we're losing Matt. Sorry, Mark.
Yeah, I think we might have. Tell you what, I can pull up the questions. Okay, hey, Antoon, I'm going to go to the next one. All right, this is a good one. Deep concepts. We mentioned not boiling the ocean. Where would you start? We talked about five categories of simulation. How do you decide where to start?
I guess I want to say focus only on your key problem. Don't try to build the magical theoretical digital twin that does everything for everything, right? So it's really easy to get lost in detail on things that don't really matter to the core of the problem you're trying to resolve. So focus on where did I have my biggest problem in my last 2 projects, and then after that, go and as you prove yourself on having solved that key aspect, then start building out and say, hey, where else could I gain benefit? Where in our specific situation is the next best thing? So walk before you run, and run before you dance, right?
Yeah, I think a key concept too is that we talked about the levels of fidelity that an equally foolish errand would be to create. You mentioned the super duper and perfect simulation. Well, if you really only care about the time it takes for your robot to perform an operation, you don't need an advanced high fidelity multi-physics polynomial equation to do this. You just need to care about that. So be focused on the problem as you state, and then what's the really minimum amount of simulation that I need for the value that I'm going to get out of that. I think that's a great way to approach this, because you can always go deeper. It's really knowing how much I need to actually simulate to get the value that I need, rather than just creating the world's best digital twin that is over-engineered.
Yeah.
Great, thanks very much. Reminder to the audience, please keep the questions coming in, and we'll get to them offline if we don't have time. Another question, can you share a specific project or company that has successfully rolled this out?
Oh, absolutely. Absolutely. We, a couple of weeks ago, we had our user group meeting in Milan. We had a company called ECM Technology out of France do a presentation. They build vacuum carburizing chambers and a whole production line for metal treatment. And this was a large facility designated to go to Ramos in Mexico, right? So it's a French OEM delivering to Mexico. It's a large facility, many chambers, shuttles moving from chamber to chamber, moving products. It was a complex system. They had to use customer PLC coding standards, which were new for the engineers. it was too large to physically replicate. It was over 1,000 square meters worth of machinery, and of course their target location was very far, so commissioning was going to be very expensive on site. So they needed to look at the electrical behavior, the mechanisms of the system. Fluid physics mattered for the mechanical seals that they were doing, and thermodynamics for the behavior inside these ovens. So they happened to used MATLAB for building the simulation on the fluids and the thermodynamics pieces, so they could model the temperature and the seals of the vacuum. They had many duplicated cells, so there were 17 of one kind and 8 of another, and they used our asset manager to go and be able to make a change once and replicate it to all 17 systems as they were learning, or all 8 of the carriers. They had robotic integration, so they had a lot of robots as part of this process, and they linked those in with Emulate3D and their robot controller. And what they loved is they had a lot less risk for the engineers, both electrical risk. At startup, they've had issues with nearly getting people electrocuted or squashed, but simply because these systems are so complex and dangerous, right? So they had a project where after design, the product and transport would take them 5 months before they could get it on site at the customer. And then normally they plan on a 10-month commissioning software and hardware debug for a project this size. What they achieved was a savings of 5 full months on the project. So before commissioning was done, they'd made so much progress, and they were so far ahead of the customer's expectation that they received 2 additional orders simply from confidence in the solution. And best of all, the guys got to come home for Christmas because they got so much time out of their commissioning cycle. So
that's the real cherry on top. So budgeted 10, normal project for them, achieved it in 5, so an incredible savings, and then the cherry on top is they get to be home for Christmas. That impact, we didn't really touch on it today, but the home more, work from anywhere, fewer flights, we call it human sustainability of just being able to work from teams in multiple locations in a shared space. That's invaluable to a lot of folks that are used to, Anthony, you mentioned you did some commissioning, used to being on site away from their family for a long period of time. Well, business and cost savings aside, the human capital that it takes to commission a project is extreme. So that's an incredible savings.
Yeah.
Great. If we can go fast on an answer, we can get one more in. How can having a digital twin help promote more regular incremental improvements rather than the set it and forget it decline?
I like this one. So Anthony, for me, quickly, I think this is the 6 month to a year factor of, now that we've been in operation, we would have designed it this way. How many times we've walked on a plant floor and heard an operator or someone giving feedback of, well, if they would have designed it this way. To me, that's the design loop, because we know you're constantly doing upgrades. At those upgrade stages, your job is to do it as quickly and efficiently and low risk as possible. But what if you could actually test those upgrades and those changes on your twin, because you still have it from when it was commissioned, and you're using that to test these pieces as you upgrade and extend that machine lifecycle? My answer.
Absolutely correct. I totally agree. Yeah.
Great. Thanks a lot for everybody, the great questions. And thanks again to our great speakers, Matt Masaryk and Antoon Lane, for sharing their time and expertise.
Thanks, Mark. Thank you, everyone.
Thank you,
All right. I'd also like to thank our sponsor, Rockwell Automation, for sponsoring today's event. And now that we're just about done, we want to hear how we did. The exit survey will pop up on the screen as soon as the webcast ends. Please take a moment to complete it, because we use this information to improve our webcasts. Finally, on behalf of Control Engineering and Rockwell Automation, I'd like to thank you for attending. This concludes our webcast. Thank you and goodbye.